Okay, to finish up section 12.7, triple integrals and spherical coordinates, we've got two more examples. So this is video 2 of 2 to complete this section. We're asked to integrate the triple integral of x squared plus y squared over a region E. And E is the region that lies between the spheres x squared plus y squared plus z squared equals 1, which is a sphere of radius 1, and this sphere of radius 2. Rho squared equals 4, so rho equals 2. So the region that lies between these two spheres, the smaller one and the larger one, is really a spherical shell. Now, that being the case, rho will range from 1 to 2 to go from the inner sphere to the outer sphere. And then to fully shape the sphere in terms of the angles, phi should travel its full range from 0 to pi. Theta should travel its full range in the xy plane from 0 to 2 pi. Recall that phi goes from the positive z-axis to the negative z-axis. So in this manner, we'll completely form both of these spheres, and then this will restrict us to the shell that's between the sphere of radius 1 and the sphere of radius 2. One thing that will help to recall is that x is equal to rho sine phi times cosine theta. We have a similar expression for y, and we'll need that to convert our integrand into terms of spherical coordinates. So with this region E represented clearly, we can write the iterated integral from 0 to pi for phi, 0 to 2 pi for theta, 1 to 2 for rho. This is x squared plus y squared from our original integral. And then our integral formula tells us this times rho squared times sine phi. So let's pause a moment with our function. We notice that rho squared sine squared phi and rho squared sine squared phi shows up twice here as multiples. So we'll factor that out away from cosine squared theta plus sine squared theta to here. What we realize we end up with is cosine squared theta plus sine squared theta is 1. So 1 times rho squared times sine squared phi. So we're just left with rho squared sine squared phi. Now this rho squared sine phi, again, it's from the integral formula. So it just held in place while we worked on the integrand itself. Now we combine like terms. We have rho to the 4th sine cubed of phi, d rho, d theta, d phi. Integrating with respect to rho first, we get 1/5 rho to the 5th from 1 to 2. Evaluating our limits of integration, that's 2 to the 5th minus 1 over 5. We push that constant out in front of the integral, and we're ready to go with integrating with respect to theta. Now, sine cubed phi is a constant function with respect to theta. So when we integrate with respect to theta, we just have theta times sine cubed phi. Then we evaluate from 0 to 2 pi. So we have 2 pi minus 0 times sine cubed phi. So again, we just have another constant within our integral. It's 2 pi. We'll factor that out to the front of the integral. And it's 62 pi over 5 here, our constant in front of the integral. Now we're integrating sine cubed of phi from 0 to pi, and we can use the trig integral of the technique of sine cubed phi equals sine squared phi times sine of phi, Pythagorean identity substitution to get 1 minus cosine squared phi equals sine squared phi, and use the extra sine phi as a part of a u substitution. Or we could just do what I did, go find a table in paper in the back of the book, or use a reduction formula if you happen to have one memorized, and we pick up this reduced version of the integral we previously had. So that's reduction formula that reduces that power of sine by 2 at a time. In this case, we get to sine to the first power of phi, which is a pretty easy integral to handle. Now, otherwise, we evaluate from 0 to pi for phi for this function as part of that reduction formula. And it turns out that sine of pi and sine of 0 are both 0. We have that marked here. So we have a 0 minus a 0. And that whole front term is just going to be a 0. The sum's inside that big bracket. And we have 2/3 times the antiderivative of sine phi is negative cosine phi from 0 to pi. So that lets us write cosine 0 minus cosine pi. The minus sign is letting us switch that order, or instructing us to switch that order. Just a quick way to handle that minus sign. Now 2/3 times our constant we've been carrying out front, cosine 0 minus cosine pi. That's 1 minus -1 in the brackets. So that's a 2. So then we have all these constants times each other. And the result of that is 248 pi over 15. Again, spherical coordinates are quite a bit something to work with. The only reason we'll do so is when we'll realize we're dealing with a region that looks very spherical or is spherical. It has a lot to do with a spherical zone, or can be expressed easily in terms of spherical coordinates. The sign that things are going along the way we'd like is right here. At that iterated integral, when we realize that all our limits of integration are constants, and there might be a moment of hesitation here until we realize that quite a bit of this simplifies, and really at the end of the day, the hardest thing we do is the integral of a power of a trig function. Okay, one more example, and this involves volume of a solid. So again, we'll use the typical volume formula for a triple integral, where we just set the integrand function equal to 1 and integrate over the region. So the solid we're given in this case is a solid that lies within the sphere x squared plus y squared plus z squared equals 4. So a sphere of radius 2, so rho equals 2. And above the xy plane and below the cone z equals square root x squared plus y squared. That's also written as z squared equals x squared plus y squared. So we've drawn the sphere above the xy plane. So this hemisphere is what we're left with that constraint, sitting on the xy plane essentially. Now inside of that is this cone, z squared equals x squared plus y squared. Now it's tempting to go after these intersections and what this circle is and all that, but if we read closely, what we want to find is the volume of the solid that lies within the sphere, so within this sphere, above the xy plane, and below the cone. Okay, so to highlight where that is more or less in perspective is really here. Of course, this is three-dimensional, but if we imagine rotating around underneath that cone, we're forming this sphere with a cone kind of sliced out of the top of it. So that's what we're interested in coming up with, is the volume in that region. To describe that region, one key thing needs to be seen. This line along the cone, blue line forming that cone, the same one over here, is at an angle of pi over 4. If you don't believe that, you can use sort of vector notation for this point here, this point on the z-axis, this point on the origin, form those two vectors, take the dot product, and determine what cosine of, or use the u dot v equals magnitude u times magnitude v times cosine theta identity to resolve that theta is pi over 4. Or you can just look at the symmetry of it and feel pretty confident that that's going to be pi over 4. So anyway, phi will range from 0 on the z-axis to pi over 4 off of the z-axis. So we've got that denoted. Actually, not 0 on the z-axis. We want the lower portion. So we want to go from pi over 4 to pi over 2 away from the z-axis. Again, this is pi over 4 from the z-axis. This is pi over 2 from the z-axis. So from below the cone down to the xy plane. Okay, so that's pi over 4 to pi over 2 for phi. Okay, now since we have the full circle on the xy plane, theta ranges from 0 to 2 pi. And then since we're dealing with the sphere of radius 2, we have a possibility of going out a full radial distance of 2 in some spaces on this, some points on that sphere. Then we need to let rho range from 0 to 2. So this makes up our entire region E that we'll need to integrate with respect to. So the volume of this region is the integral over the region of the function 1. Same trick we've been using all along. Now, limits of integration are per what we've got in our set describing E. And we don't forget to include our rho squared sine phi from our integral formula. And then d rho, d theta, d phi. We integrate with respect to rho first. Rho squared becomes 1/3 rho cubed. evaluate from 0 to 2. That's 2 cubed minus 0 cubed times 1/3. It's a constant, so I've already moved it out of the integral. It's 1/3 times 8. Now we're integrating sine phi with respect to d theta. Sine phi is a constant with respect to the variable theta. So we just arrive at theta from 0 to 2 pi. Limits of integration for that. That's 2 pi minus 0. Again, that's a constant, so we'll move that in front of the integral as well. Here it is out front, times the 8/3 that we already have out front. And now we're integrating sine of phi with respect to phi from pi over 4 to pi over 2. Antiderivative of sine of phi is negative cosine of phi. Negative cosine of phi from pi over 4 to pi over 2 times our constant. And the minus sign in front of cosine phi just has us swap our orders. It'll be cosine pi over 4 minus cosine pi over 2. Cosine pi over 4 is root 2 over 2. Cosine pi over 2 is 0. So 16 pi over 3 times root 2 over 2 leaves us with 8 pi root 2 over 3. And that's it for a volume problem. So spherical coordinates are useful when we're dealing with things that are just very easily expressed in terms of spherical coordinates. We can use it for other things, but if we don't have constant limits of integration, there's a good chance maybe we don't want to go to spherical coordinates for such a problem.